lesson is an introduction to drag. Introduction. When objects move through a fluid, they experience a resistance to their motion. This force, or the resistance, is called the drag force. In introductory mechanics, we just ignore drag because it complicates our measurements of force and movement. But ignoring this everyday force makes a lot of physics seem really dumb. For example, let's say that we have a feather and a penny, and we're going to drop them from the same height. Let's assume that they have the exact same mass. If you don't account for drag, then of course they land at the bottom at the exact same time because they have the same acceleration. But even a kindergartner could tell you that that's just silly, and that of course the penny will win the race. If I plot the trajectories of the penny and the feather as it falls, you can see here that the penny in green is falling further and further during each time interval, and the feather is just falling the same exact distance during the time interval. And so if we really want to model the motion of objects, we're going to have to figure out how to model this fluid resistance or this drag force so that we can find the correct equation of motion. The problem is that drag is extremely hard to model and find the exact equation. Depending on the velocity of the object or the properties of the fluid, the drag could be different. In one scenario, the dominant source of the drag may be due to the inertia of the fluid in front of the object. In this case, the object has to exert a force on the block of air or fluid in front of it in order to accelerate that volume of fluid to some fraction of the object's speed. Essentially, the object's accelerating the fluid so that it will just move out of the way. In another scenario, the dominant source of drag may be due to the frictional force between adjacent layers of the fluid as the object shears one layer with respect to the other layer. Maybe in other cases, both sources of drag are present. Thus, it turns out that if we want to model drag, we're going to want to use an approximation. There's only one goal in this lesson, and that's to be able to approximate the drag force using a series. In this lesson, we'll mostly be talking about using a Taylor series. Our text of reference will be Classical Mechanics by John Taylor, Chapter 2, Section 1. The first goal is to approximate the drag. We said that the drag force F is a force that resists the motion of an object. That means that the drag force will act in the direction that is opposite of this velocity v. In addition, the drag force should be a function that is dependent on the velocity. If the velocity increases, so should the drag. Mathematically, we can write the drag force as just being equal to the minus of f of v times v hat, where this v hat is a unit vector that points in the direction of the velocity. V hat is just given by the velocity vector divided by the speed. However, like we said in the introduction, it's hard to write a more exact equation than what I've just written here. That's because the nature of the interaction of the drag force changes with the velocity and the properties of the fluid. So instead of writing an exact equation, let's take our experimentally measured parameters and approximate a function for the drag force. But before we do this, let's talk about just approximating a function. To approximate a function, any function, you need to define the range of the function that you would like to approximate. Here I've cut out this section, as this will be the function that we will approximate. Second, you need to add a series of other functions together to get an approximate function. If you use a Fourier series, then you add a series of sine and cosine waves. And if you use a Taylor series, then you add a series of polynomials together. Here, I'll use a Taylor series and I'll add polynomials. I'll show the functions that I'm adding as orange functions over here on the right. Their sum I'll display as this green curve on the left. Now I have a line and a quadratic. And finally now I have a line, a quadratic, and a cubic. Here's their sum over here on the left. As you can see, if I add more functions together, I get closer and closer to the original function, and my approximation gets better. In a Taylor series, the more polynomials we use, the better the approximation. If you have many slope changes in your original function, then you're going to need higher and higher order polynomials in order to capture that behavior. Mathematically, we see that a Taylor series can be written in this form, where the a's are all constants. You can see here that I'm adding a series of polynomials. If a equals 0, then the series is called a Maclaurin series. We are going to use the Maclaurin series to approximate the drag force. We could have picked a Taylor series or a Fourier series, but it turns out that the Maclaurin series is simpler, and the constants in the equation can be easily related to the fluid properties. So let's go ahead and use a Maclaurin series to approximate our function f of v. If we use a Maclaurin series, we get a function f of v that's equal to a0 plus a1v plus a2v squared plus a3v cubed, and so on. But we can go ahead and simplify this even more, because we know that f of v is going to be 0 when v equals 0, and thus this a0 term is really going to drop out of the equation. In addition, the experimental data for drag shows that for everyday velocities less than the speed of sound, we only need to keep up to the quadratic term. Given this information, we can rewrite f of v. Here I've rewritten f of v using this information, and I've also replaced the constants a1 and a2 with the more commonly used constants b and c. If we plug this back into our original equation for the drag force, we get that the drag force is equal to negative bv times v hat minus cv squared times v hat. We are now ready to use this approximation in our expressions for Newton's laws to solve for the equation of motion of an object. We will be doing this in class over the next 2 weeks. So to make sure you understand this derivation, let's do some problems. In the first problem, let's look at the drag force equation and determine when each term will dominate. Go ahead and figure this out. It turns out that at low velocities, the linear term will dominate over the square, and that at high velocities, the square term will dominate over the linear term. In mid-range velocities, you'll end up with both terms. But what's high and what's low? We'll talk about that in our first lecture on Tuesday. In the next problem, let's ask if the constants b and c could be negative. Could they be negative? Why or why not? No, these constants can't be negative. The original constants a1 and a2 could be negative, but these ones, b and c, are defined to be positive. That way the drag force always points in the direction opposite of the velocity. Let's do some more problems, but this time let's focus more on the Taylor series. In this problem, we're going to talk about the Taylor series. You've probably used Taylor series before, but perhaps in a different context. Typically, they are used to approximate a function near a particular x value, namely x equals a. We were using them to find an approximate function for an experimental data set. However, if you want to approximate a function, you should use this second definition. That's because if you already know the mathematical equation for the function, you can use the derivatives in order to find your Taylor series. Show that this second definition for the Taylor series is completely equivalent to the first definition. To figure out this problem, you're going to want to start by computing the derivative of f. If we compute the derivative of f, we get that f prime is equal to a1 plus 2a2 times the expression x minus a plus 3a3 times the square of x minus a, and so forth. Given this equation, we note that f prime of a is just equal to a1. And so by computing this derivative, we find the value of the very first constant. Let's continue to do this and see if we can find the rest of the constants. The second derivative is just going to be 2 times a2 plus 3 times 2 times a3 times the expression x minus a, and so on. F double prime of a is just going to be 2 times a2. If we calculate more derivatives, we can find the rest of the constants a3 through an. If we were to substitute these constants back into our original equation, we would of course get this second definition for the Taylor series. So yes, these two equations are completely equivalent. It turns out that the two equations are just used for different purposes. When we have an experimental data for f of x, and we would like to find the approximate function, then we want to use this first equation, because it allows us to easily fit the experimental data and determine the constants a0 through an. On the other hand, if we have a mathematical expression for f of x, then we really just want to find the derivatives of f of x and plug them in order to get our approximate function. What's interesting is that in both cases we find an approximate function by using the slope at a particular point, the point x equals a, to essentially compute the values for the function near f of a. In this next problem, let's build on our knowledge of the Taylor series. In this problem, I want you to find the approximate function for sine theta at small angles using a Taylor series. Many times in physics you'll find a problem like this one, where you have to find the approximate value for a function near 0. Go ahead and expand this sine theta using the Taylor series. In this problem, you want to expand sine theta using a Taylor series centered at x equals 0. This is, of course, just a Maclaurin series. We use the second definition of the Taylor series and plug in our function as sine theta. Then, on the right-hand side, we plug in the values for all of the derivatives and for our expressions for theta. When we do this, we find that sine theta equals 0 plus theta plus 0 plus theta cubed over 3, and so on. Typically, we'll just truncate the series in order to keep an approximate value. Here I've truncated it at theta cubed over 3. Typically, for the small angle approximation, we'll a lot of the time just truncate it at theta. Hopefully you've seen this small angle approximation before in introductory physics. It's really interesting how useful this Taylor series really is. Knowing how to use a series to approximate a function will be really useful in your scientific life. For now, you'll just need to know how to approximate the drag force. Conclusion. Today we focused on approximating the drag force using a series. We'll need this approximation in order to solve for the equation of motion for objects where drag is important. This approximation will now allow us to predict the actual motions of projectile objects or other objects moving through fluids. That's it.